So when we last left off, we discussed methods to perform mass mole conversions. What we're now going to talk about are the methods to calculate and determine empirical and molecular formulas. So let's talk a little bit about where these names are derived from. Most analytical methods, or most methods that we use in the laboratory, will provide us either a mass or mole ratio of elements in a sample, or these analytical methods are typically able to provide us the mole and mass percent of elements in a sample. Okay? The mass percent, mole percent, mass ratio, or mole ratio are instrumental and can be used to calculate what's known as the empirical formula. Now, because many analytical methods only give us the elemental composition as a percentage or as a ratio, the formula we calculate from many of these experimental or empirical methods is that of the empirical formula. So the empirical formula is the simplest formula that contains the smallest whole number ratio of elements that make up a compound. So the empirical formula can be thought of as the simplest whole number ratio of elements. So the empirical formula can also be thought of as the smallest whole number mole ratio of each element. So to give you an example of how we can convert, for example, a long-form molecular formula into an empirical formula, let's look at these two examples. So for P2O10, we have 10 moles of oxygen for every 2 moles of phosphorus. Now, we can simplify this 10:2 ratio. And if we're writing the empirical formula, we want the simplest mole ratio. Thus, this 10:2 could be simplified to what ratio?
5:1.
Yep, exactly right. So we can simplify this to 5 moles of oxygen per 1 mole of phosphorus, giving us an empirical formula of PO5. So as we can see, the empirical formula is the simplest mole ratio, simplest whole number mole ratio of elements. So for example, in C3H6, we have 6 moles of hydrogen per every 3 moles of carbon. And that in turn simplifies to a 2:1 ratio, 2 moles of hydrogen per 1 mole of carbon. So then we can rewrite this formula as an empirical formula, where our empirical formula, our simplest whole number mole ratio of elements, would be CH2. Now, typically, once we have determined the empirical formula experimentally, a separate experiment is done to get the molecular weight and determine the molecular formula. The molecular formula is a little more straightforward. It's just the number of atoms of each element in a compound. Now, what's really interesting is that molecules can have the same empirical formula while having different molecular formulas. So let's compare N2O4 and NO2. So in N2O4, we have 4 moles of oxygen per 2 moles of nitrogen. This is our molecular formula. In NO2, we have 2 moles of oxygen per every 1 mole of nitrogen. However, if we look at the empirical formula, N2O4 has an empirical formula of NO2 with 2 moles of oxygen per 1 mole of nitrogen. As we can see, N2O4 and NO2 both have the same empirical formula while having different molecular formulas. Thus, if we want to accurately determine the formula of a compound and accurately determine the molecular formula of a compound, we need both the empirical formula and the molecular weight. So we need some additional information to take our empirical formula and convert it into a molecular formula, because many compounds can have different molecular formulas with identical empirical formulas. Does that idea make sense to everyone? Now, if we think a little bit about the empirical formula, you can think of it in this way. The empirical formula is repeated n times, where n is a whole number, to give the molecular formula. N can be thought of as the number of empirical formula units. So for example, if we have an empirical formula unit of CH2, let's write that out. So let's suppose this is our empirical formula unit. And let's suppose we have 3 empirical formula units. Okay, we'd have CH2, 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 which we can simplify to a molecular formula of C3H6. Does everyone see how the number of empirical formula units in our empirical formula can be used to calculate the molecular formula? Does everyone see that relationship? Does that idea make sense?
Yes.
Okay, so if we have the number of empirical formula units and we have the molar mass or the molecular weight of our entire compound, the molar mass can be thought of as the total mass of each of these empirical formula units. Thus, if we know our molecular weight, this is from our molecular formula, and we know our empirical formula unit mass that we get from our empirical formula, we can calculate the number of empirical formula units. This is really important because once we have the number of empirical formula units, we can take our empirical formula and convert it to a molecular formula. So let's show an example. So we're given the empirical formula of hydrazine is NH2, and its molecular mass is 32 gram per mole. We're asked, what is the molecular formula of hydrazine? So NH2, that is our empirical formula unit. Let's calculate the molar mass of this empirical formula unit. So for NH2, calculating the molar mass, we have 1 mole of nitrogen, 14 grams per mole of nitrogen. That's from the periodic table. We have 2 moles of hydrogen and 1 gram per mole hydrogen. Punching this into our calculator, we get a molar mass of 16 gram per mole of NH2. Okay, so we have our empirical mass. So now we can calculate N. So to calculate the number of empirical formula units, we take our molecular mass and we divide it by our empirical formula unit mass, 32 over 16, that gives us an N value of 2. So to calculate our molecular formula, We write out our subscripts for our empirical formula, and we multiply each of our subscripts by n. That in turn gives us a molecular formula of N2H4. Does this process make sense to everyone? Does this process for calculating empirical and molecular formulas make sense? Okay, so let's keep going then. And let's try to apply what we've learned to the following example. So we're given the empirical formula of benzene is CH, and its molecular mass is 78 gram per mole. And we're asked to calculate the molecular formula of benzene. So let's work through this example over the next 3 to 4 minutes. And then I'd like students to share their proposed responses in the chat, verbally, or annotated on the class whiteboard. And I'd like to see multiple students sharing their proposed molecular formulas for benzene. So let's work through this example, and then we'll discuss in 3 to 4 minutes. So as we work through this example, does anyone have an initial thought or idea? Would anyone like to share any of their initial approaches to tackling this problem? So we're given our empirical formula unit, and we're given our molecular formula. So we have all the tools that we need here to calculate our molecular formula. What I would like is for students to start sharing some of their initial thoughts and steps, or sharing their final calculated molecular formula. So, as we tackle this problem, would anyone like to share their calculated empirical formula mass? So we know we have our empirical formula unit as CH. Would anyone like to share their calculated molar mass for this CH subunit? Yep, 13 gram per mole. We have 12 grams from carbon, 1 gram from hydrogen. So this CH unit has a mass of 13 gram per mole. Okay, so now that we have that information in hand, would anyone like to try and propose how many empirical formula units do we have? What is the value of N for benzene? So let's work through this example. Would anyone like to share their thoughts on how many empirical formula units do we have? What is the value of N? Given that we know that our molecular weight for benzene is 78.0 gram per mole. Great. As we see in the chat, one student shared that they calculated our number of empirical formula units to be 6. We obtain the number of empirical formula units by taking our molecular weight and dividing by the molar mass of our empirical formula unit, which is 13 gram per mole. Units of gram per mole cancel, and we're left with a value of N of 6. So that tells us we have 6 of our empirical formula units. So putting this all together, what is our final molecular formula? What is our final molecular formula? C6H6, exactly right. We take our empirical formula subunits, multiply each of our subscripts by N, and that gives us our molecular formula. Does that make sense to everyone?
Yes.
Perfect. Okay, we've seen how we can take the molar mass and take the empirical formula and use those two values to calculate the molecular formula. Now, we're going to talk a little bit about how we can directly calculate the empirical formula given the mass percentage or mole percentage of each element in a compound. Okay, so let's take a look. Let's take a look at a compound with two elements that I'll call element 1 and element 2. Each of these compounds will have a mass of each element. So we'll call mass 1 the mass of element 1. Mass 2 will be the mass of element 2. That'll abbreviate it as M1 and M2. Additionally, each of these elements will have a mass percentage. So the mass percentage of element 1 can be defined as the mass of element 1 over the mass of element 1 plus the mass of element 2 times 100%, because this compound just has two elements. We can also write the mass percentage of element 2 as mass 1 over mass 1 plus mass 2 times 100%. Now, the reason why we're talking about this and the reason why we're looking at this example is I'm going to show you a general way to calculate the empirical formula from any mass percentage. But to do that, we're going to need to show algebraically how we get this final equation. So if we have a typical compound that has two elements, we can write the mass of each element as mass 1 and mass 2, and we can write out the mass percentages. We can also think of this mass percentage as the mass 1 over the total mass, right? Since that's what mass percentage is. Okay, so we have all this information in hand. And if we want to calculate the empirical formula, so our goal when we're calculating the empirical formula is to get the ratio of the moles of element 1 over the moles of element 2. The empirical formula fundamentally is the simplest whole number mole ratio of elements. Let's write this as mole 2 over mole 1 just to make things a little more straightforward. Okay, so if our goal is to get the mole ratio, let's take a look at what we have and let's show how we can calculate the moles. Well, we know that the moles of element 1 can be calculated from the mass. So I can take the mass of element 1 over the molecular weight of element 1. I can calculate moles easily from that. I can also calculate the moles of element 2 by taking the mass of element 2 over the molecular weight of element 2. So all we've done so far is just restated some common equations that we've used throughout the course. We know we can calculate the mass percentage of each element. We know we can calculate the moles of each element given the mass and molar mass. Does this make sense to everyone so far?
Yes.
Now, you could, of course, go through these empirical formula calculations stepwise, right? If we want to calculate the moles, we need the mass, and we can calculate the mass by taking the mass percentage. So let's show how we calculate the mass. We know that mass percentage corresponds to the mass over the total mass times 100%. And we can take this equation and rearrange it to solve for mass 1, right? Mass 1 is equal to the mass percentage over 100% times the total mass. Now, in most cases, we will not be given the total mass of sample we're studying. And what's pretty interesting, and what we'll see in a moment, is that the total mass of sample doesn't matter when you're calculating the empirical formula. The only thing we care about is the mass percentage. We'll show that in a moment. If you wanted to do calculations stepwise, you can assume any total mass, though it's often convenient to assume 100 grams. That's how the book commonly teaches you to calculate the empirical formula. You solve for the mass using the mass percentage, assuming a total mass of 100 grams. You can pick any total mass you want in reality. Does everyone see how we rearranged this equation to solve for the mass of element 1? Does that make sense to everyone? We can calculate the mass of an element from the mass percentage and the total mass. Does that make sense? Now, by the same token, we can do this same calculation to solve for the mass of element 2, which is we can solve for from the mass of element 2 given the mass percentage. So the mass percentage of element 2 is the mass of element 2 over the total mass times 100%. Solving for the mass of element 2, we get the mass of element 2 is equal to the mass percentage of element 2 times the total mass over 100%. Okay, so this is where we're at so far. We want to calculate the empirical formula, which is the simplest mole-to-mole ratio. To calculate the moles of each element, we need the mass and the molar mass. The molar mass we can just get from the periodic table. The mass we can get from the mass percentage. Now, all we have to do is start substituting. So in this case, we know that we can substitute the mass of element 1 into this mole expression. So we know the moles of element 1 can be rewritten as the mass percentage of element 1 over 100% times the total mass divided by the molar mass of element 1. We can also write the moles of element 2 as the mass percentage of element 2 over 100% times the total mass over the molecular weight of element 2. Does that substitution make sense? All we did was plug in the mass into our mole equation. Now, from here, we can simplify. We know the empirical formula is best thought of as the mole-to-mole ratio of our two elements. So then, all we have to do is substitute in what we've calculated into this mole-to-mole ratio. So, we'll take the moles of element 2, which corresponds to the mass percentage of element 2, over 100% times the total mass over the molecular weight of element 2, divided by the moles of element 1, which corresponds to the molecular weight of element 1 over the total mass times 100% over the mass of element 1. Now, as we can see, we notice something very interesting. The total mass and this 100% value cancel out when we look at our mole-to-mole ratio. Thus, we get for our empirical formula, which is our mole-to-mole ratio, the empirical formula can be calculated from the mass percentage and molar mass. And we see algebraically that we can calculate our mole-to-mole ratio, we can calculate our empirical formula by taking the ratio of the mass percentage over the molar mass. So we've seen algebraically that we can solve for the mole-to-mole ratio, and we can get a very simple equation to calculate the empirical formula from the mass percentage and the molar mass. Does this make sense to everyone? Does everyone see how we obtained this equation? Any questions on this thought process? Okay, so we know that we can calculate the empirical formula directly using this equation. What I want to highlight now is an alternative algebraic method or a stepwise method for calculating the empirical formula. So first, if you're going to use the algebraic method, first you want to identify the mass percentage of each element and the molecular weight of each element. So let's suppose you have the mass percentage of element 1, the molecular weight of element 1, the mass percentage of element 2, and the molecular weight of element 2. Now, if you don't just want to directly use this equation that we've prepared, you can instead calculate this stepwise. Next, you can calculate the mass of each element, assuming a total mass of 100 grams. So we know that the mass of element 1 would be equal to the mass percentage over 100 times the total mass. Plugging in a total mass of 100 grams, we get the mass is going to be identical to the mass percentage. We can repeat this process for our second element. Again, we're solving for the mass of each element using the mass percentage and the total mass. Okay, so now that we have the mass of each element, we're next going to calculate the moles. So we can calculate the moles of each element using the mass and the molar mass, right? We can calculate the moles of element 1 by taking the mass of element 1 over the molar mass. So we can do that by taking the mass percentage in this case over the molar mass. We can repeat this process for our other element. Take the mass of element 2 in this case, over the molar mass of element 2, which is equivalent to the mass percentage of element 2 over the molar mass of element 2. So if you're doing it stepwise, you're then going to calculate the moles of each element and finally calculate the mole to mole ratio. And this mole to mole ratio is going to be your empirical formula. So in this case, we're going to take N2 over N1, which we see corresponds to the mass percentage of element 2 over the molar mass of element 2 times the molar mass of element 1 over the mass percentage of element 1. So you're welcome to either use the equation method or the stepwise algebraic method. Both methods are valid, and it's really up to your personal preference which method you find most useful. Does this make sense to everyone? Do these methods for calculating the empirical formula make sense? Any questions on the two methods to calculate the empirical formula? Either the direct method using an equation that we've derived, or the algebraic method where we do a series of stepwise calculations. Any questions before we try to apply what we've learned? Okay, so let's try to apply what we've learned and let's showcase how we would calculate the empirical formula and the molecular formula for the following example. So we're given that a sample was found to be 24.8% carbon, 2.079% hydrogen, and 73.1% chlorine by mass. The sample has a molar mass of 290 gram per mole, and we're asked to determine the empirical and molecular formula. So let's start with our empirical formula. And let's apply what we've learned in the algebraic method. So first things first, we need to identify our mass percentages and our molar masses of each element. So we know the mass percentage of carbon is 24.8%. We also know that the mass percentage of hydrogen is 2.079%. And finally, we know from this problem the mass percentage of chlorine is 73.1%. Let's now read off the molar masses. The molar mass of chlorine is 35.45 gram per mole. The molar mass of hydrogen is 1.0079 gram per mole. The molar mass of carbon is 12.01 gram per mole. Okay, so I've written out all the baseline information I'm going to use for this problem. The next thing I'm going to do is I'm going to calculate the mass of each element, assuming 100 grams total. So I'm going to write that as in my assumption box and just note I'm assuming 100 grams total. So the mass of carbon would be the mass percentage of carbon over 100% times the total mass. Substituting, the mass of carbon would be 24.8% over 100% times 100 grams. That gets us 24.8 grams of carbon. We can repeat this calculation for the mass of hydrogen, where we take its mass percentage, which is 2.079% over 100 times 100 grams. That in turn gives us a mass of hydrogen of 2.079 grams. Finally, we can calculate the mass of chlorine, again, by taking the mass percentage over 100 times 100 grams. And that in turn gives us a mass of chlorine of 73.1 grams. So now that we have each of our masses, if we're looking for the empirical formula, we need the simplest mole ratio of elements. We want the simplest ratio of moles. So then our next step is to calculate the moles. So for the moles of carbon, we're going to take the mass of carbon over the molar mass. Punching this into our calculator, when we divide the mass by the molar mass, that in turn gives us 2.065 moles of carbon. Okay, we can repeat the same process for hydrogen. So punching this into our calculator, we get 2.065 moles of hydrogen. Now let's do the same process to calculate the moles of chlorine. We have 73.1 grams of chlorine over 35.45 gram per mole chlorine. That in turn gives us 2.065 moles of chlorine. Does this process make sense to everyone so far? We identify our mass percentages and molar masses. We calculate the mass of each element, assuming 100 grams total. And then we calculate the moles of each element by using the mass over the molar mass. Does that make sense to everyone?
Yes.
Perfect. So now that we have the moles of each element, we're going to calculate the empirical formula by taking the mole to mole ratio. And I find the easiest way to get a whole number ratio of elements is to divide by the smallest number of moles. So I'm going to arbitrarily divide both of my mole values by the moles of hydrogen, because the moles of hydrogen in this case is the smallest mole value, because all of these values are equal. So you really could pick any mole value. You generally want to divide by the smallest because it's the fastest way to get a whole number mole to mole ratio. Okay, so we're going to take the moles of carbon and we're going to divide by the moles of hydrogen. Okay. So we have 2.065 moles of carbon over 2.065 moles of hydrogen. That simplifies into 1 mole of carbon per 1 mole of hydrogen. So a 1-to-1 ratio. By the same token, we can take the moles of carbon. Well, in this case, we have to divide chlorine. So moles of chlorine over the moles of hydrogen. So in this case, we have 2.065 moles of chlorine divided by 2.065 moles of hydrogen. Again, we have a 1-to-1 ratio. 1 mole of chlorine per 1 mole of hydrogen. So based on this ratio of elements, we can write out our empirical formula. So as we see, we have 1 mole of carbon per every 1 mole of hydrogen per every 1 mole of chlorine. And that in turn gives us an empirical formula of CHCl. Does that process make sense to everyone? Does that process make sense? Now, in order to complete this problem, if we're given the sample has a molar mass of 290, we actually have all the tools that we need in order to calculate the molecular formula. So let's tie these two parts together. So we have a molar mass of 290 gram per mole. We can calculate our empirical mass by taking the mass of carbon plus the mass of hydrogen plus the mass of chlorine. Adding this up, we have an empirical mass of 48 gram per mole. From here, we can calculate N by taking our molar mass over the empirical formula mass. So we have 290 gram per mole divided by 48 gram per mole. So we have 290 over 48. That gives us an N value of 6. So tying this all together, that in turn would give us a final molecular formula of C6H6Cl6. Does this example make sense to everyone? Does everyone see how we can go from the mass percentage to the mass, to the moles, and finally to the empirical formula? Once we have the empirical formula, we can connect it with what we've learned in terms of calculating the molecular formula. We can solve for n and then convert our empirical formula to our molecular formula. Does this process make sense to everyone? Any questions on this example? Okay, so let's do another example and let's really just showcase again how we can calculate the empirical formula. And this time I'd like us to try solving this example together as a class, following the steps for this stepwise method. So let's read through this example together, and then I'd like you to work through each of these steps, and I'll check up on the class periodically. So a sample was found to be 40.7% carbon, 5.1% hydrogen, and 54.2% oxygen by mass. The sample has a molar mass of 118 gram per mole. In this case, we're asked to calculate the empirical and molecular formula. Okay, so following our step-by-step guide, since we're given the mass percentage of each element in a compound, you can obtain the empirical formula by converting the mass percentage to a mass, assuming a total mass of 100 grams. So let's work on, right now, calculating the mass of carbon, hydrogen, and oxygen in this sample. So let's look at the mass of carbon, the mass of hydrogen, and the mass of oxygen in this sample. So let's take about 2 to 3 minutes, and I'd like us to try and calculate the mass of carbon, hydrogen, and oxygen in this sample, given the mass percentages. So let's start off with that first step. So we're given the mass percentage and we can assume a total mass of 100 grams. So what would the mass of carbon, hydrogen, and oxygen be in this sample? So let's work through this first part together as a class, and we'll discuss as students share their responses. So we know we can calculate the mass of each element given the mass percent and the total mass. So if we're assuming a total mass of 100 grams, would anyone like to share their proposed mass of carbon, hydrogen, or oxygen? So let me do an example to help spark this discussion. So we know we can calculate the mass of carbon from the mass percentage, which is 40.7%, and the total mass, which we were going to assume is 100 grams. That in turn gives us a mass of carbon of 40.7 grams. With that example calculation in mind, what would the mass of hydrogen be in this sample? What would the mass of hydrogen be in this sample?
5.1.
Yep, exactly right. We can calculate the mass of hydrogen by taking the mass percentage of hydrogen over 100% times 100 grams. That in turn gives us a mass of hydrogen of 5.1 grams. Okay, by this same logic, what would the mass of oxygen be?
$54.2.
Exactly. We take our mass percentage of oxygen and multiply by the total mass, which is 100 grams. That in turn gives us a mass of oxygen of 54.2 grams. Okay, does this first part of calculating the empirical formula make sense? So we've calculated the mass of each element.
Yes.
Okay, so now that we have the mass of each element, we have to convert the mass to the moles. And we do that by taking the mass over the molecular mass or molar mass of each element. So, given that we have the mass of carbon, hydrogen, and oxygen, and we can look up the molar mass in the periodic table, let's take a few moments and let's try to calculate the moles of carbon, hydrogen, and oxygen. So let's work through this next phase for this empirical formula calculation. And then I'd like students to share their proposed calculated moles of carbon, hydrogen, and oxygen in the chat, verbally, or annotated on the class whiteboard. And if there are any questions, don't be shy to ask, and I'd be happy to provide clarification as we work through these examples. So, would anyone like to share their calculated moles of carbon? Or would anyone like to share that in the chat or annotate it on the class whiteboard? So let me do another example. So in this case, if I wanted to calculate the moles of carbon, I'd take the mass of carbon over the molar mass, which is 12 grams per mole. Punching this into my calculator, that in turn gives me 3.39 moles of carbon. So with that example in mind, would anyone be able to share their calculated moles of hydrogen and oxygen?
$5.1 for oxygen.
5.1 for oxygen?
Oh,
Okay. Oh, for oxygen or hydrogen?
Hydrogen, sorry.
No worries, no worries. So we can calculate the moles of hydrogen by taking the mass of hydrogen over the molar mass. And that in turn gives us 5.1 moles of hydrogen. Wonderful, that's exactly correct. Now, what about the moles of oxygen? How many moles of oxygen do we have?
3.39.
Okay, and we obtain that by taking the mass of oxygen, which is 54.2 grams, over the molar mass of oxygen, which is 16 grams per mole. And that in turn gives us 3.39 moles of oxygen. Does this second step of the calculation make sense, where we've calculated the moles of each element? Okay,
Yes.
so now that we have the moles of each element, we generally want to choose the element with the smallest number of moles and divide the moles of every element by the moles of the chosen element. Okay, so in this case, we have a tie between carbon and oxygen. So we're just going to arbitrarily pick carbon. Okay, so in this case, we're going to write out our moles of hydrogen, and we're going to look at the ratio of the moles of hydrogen per mole of carbon. Okay, so for the moles of hydrogen, we've established that we had 5.1 moles of hydrogen. For the moles of carbon, we established we had 3.39 moles of carbon. That in turn gives us a ratio of 1.5 moles of hydrogen per every 1 mole of carbon. Would anyone like to share the ratio for the moles of oxygen per mole of carbon? So if we punch this into our calculator, what is the mole to mole ratio of oxygen to carbon for this example in particular? What is our mole to mole ratio of oxygen to carbon?
1.5 to 1.
For oxygen to carbon? Let's punch in some numbers. So for oxygen, we know that we have
Hydrogen was, yeah.
39 moles of oxygen. And for carbon, we have 3.39 moles of carbon. So what mole to mole ratio would this simplify to?
1 to 1.
1 to 1, exactly right, exactly right. So we're almost there. We almost have our empirical formula. We have 1 mole of oxygen per 1 mole of carbon. Okay, so we're almost ready to go here. However, we notice that we don't have a whole number ratio of elements. So we have to fix that. And we have to fix that using a trick, almost identical to what when we started to talk about the formulas of ionic compounds. So if the mole ratios are not whole numbers, multiply all mole ratios by the same whole number to give the smallest whole number ratios. So if we have 1 mole of carbon, we have 1.5 moles of hydrogen, and we have 1 mole of oxygen. To make this a little easier to see, you can also think of this moles of hydrogen as 3/2 moles of hydrogen. Okay, so if we want to get rid of our fraction and we only want a whole number of moles of each element, we want a whole number mole to mole ratio, what should we multiply each of these moles by? If we want to get rid of this fraction of 3/2, what should we multiply each of our moles by? What whole number would get rid of this fraction?
2.
2. So we're going to multiply each of our moles by 2. That in turn gives us 2 moles of carbon, 3 moles of hydrogen, and 2 moles of oxygen, which gives us an empirical formula of C2H3O2. Does that make sense to everyone?
Yes.
Perfect. Now, I've provided you a table on this page of common fractions and the whole number you should multiply by. In this case, we had 0.5, which corresponds to 1/2. So we multiplied all of our mole ratios by 2. Does this logic make sense to everyone?
Yes.
Okay. So now that we have our empirical formula, which is C2H3O2, we have our empirical formula set up. Since we're given the molecular weight, we can calculate N. So going all the way back to the start of this problem, going all the way back, we're given that our molar mass was 118 gram per mole. Okay, so let's write that down. We are given that our molar mass for this molecular compound was 118 gram per mole. We can calculate the molar mass of our empirical formula unit by adding up the mass of each element. Carbon has a mass of 12 gram per mole. We have 2 carbon atoms. Hydrogen, 1 gram per mole. We have 3 hydrogen atoms. Oxygen, 16 gram per mole. We have 3 oxygen atoms. So the molar mass of our empirical formula unit would be 12 times 2 plus 3 plus 48. And that gives us a mass let me just check I did that correctly.
2 oxygens.
Yeah, there we go. Perfect. So we have 12 times 2 plus 3 plus 32. That gives us an empirical mass of 59 gram per mole. So with these two pieces in hand, what is our value of N in this case? What is our value of N in this case?
2.
2, exactly right. We take our molar mass, which is 118 gram per mole, and we divide it by our empirical formula unit mass, which is 59 gram per mole. That gives us a value of N as 2. Finally, we multiply each of our subscripts in the empirical formula by N. So we have C2H3O2. We multiply each of these subscripts by N, and that in turn gives us a molecular formula of C4H6O4. And we just rewrite that final formula. Does this process make sense to everyone? Is this example making a little bit more sense as we've done a few examples where we've calculated empirical and molecular formula?
Yes.
Perfect. So let's try to apply what we've learned to this next example. And I'd like us to take what we've learned and I'd like us to determine the empirical and molecular formula for the following compound given the mass percentages and its molar mass. So this is really one case where, as there are multiple steps in the calculation, I'd like students to attempt this example And I'd like students to share each of their steps of this calculation. So for example, if you calculate the mass of an element, let me know and I'll share it on the class whiteboard. If you calculated the moles, let me know and I'll share it on the class whiteboard. And I want us to collaboratively solve this example by sharing our thoughts and responses as we work through this problem. And if you'd like me to annotate any of your written work, you can share a photo of your work in the chat. You can explain your process verbally, or you can annotate directly on the class whiteboard. This is the type of problem that you would likely see on exams. So it's important that we're able to calculate the empirical formulas. So as we work through this example over the next 4 to 5 minutes, would anyone like to share some of their initial thoughts? So considering our initial process, where if we want to calculate the empirical formula, which is a mole to mole ratio, we'd first want to state each of our given values. So we know that for carbon, we have a mass percentage of 38.7%. And we know the molar mass of carbon is 12 gram per mole. We know for hydrogen, we have 9.7% hydrogen by mass. Hydrogen has a mass of 1 gram per mole. Oxygen, our sample is 51.6% oxygen by mass. Oxygen has a mass of 16 gram per mole. With this information in mind, we can now approach the next step, which is calculating the mass of each element. So, would anyone like to start us off with this process by sharing their calculated mass of carbon, assuming 100 grams total mass? Would anyone like to start us off on this calculation by sharing their calculated mass of carbon? So we have the mass percentage of carbon, and we know that we can assume 100 grams total. Thus, what would our calculated mass of carbon be in this sample?
38.7.
Yep, exactly right. So we can calculate the mass of carbon by taking the mass percentage over 100% times the total mass, which is 100 grams. That gives us a mass of carbon of 38.7 grams. By the same token, we should be able to calculate the mass of hydrogen. And what mass of hydrogen would we have in this sample?
$51.6.
Oh,
7. Sorry.
no worries. For hydrogen, it would be 9.7 because we have 9.7% hydrogen by mass. We divide by 100% and we multiply by our total mass of 100 grams. That gives us a mass of hydrogen of 9.7 grams. You are correct that for oxygen, the mass of oxygen would be 51.6 grams. That is correct. Okay, so now that we have the mass of each of our elements, we can then calculate the moles. So what would our moles of carbon be? Let's take a few moments, and I'd like students to share their responses in the chat, verbally, or annotated on the class whiteboard. What is our moles of carbon given our mass of carbon?
.23.
Yep, exactly right. So for our moles of carbon, we take our mass of carbon over our molar mass. Punching that into our calculator, that gives us 3.225 moles of carbon. I would recommend not rounding until the end, especially in empirical formula calculations where small rounding errors can make a huge difference. Does this make sense to everyone so far?
Yes.
Okay. Would anyone like to continue on and advance our discussion by sharing their calculated moles of hydrogen? How many moles of hydrogen do we have in this sample?
.7.
Exactly. 4.7 or 9?
9.7, sorry.
No worries. So for our moles of hydrogen, we have 9.7 grams of hydrogen, and we have a mass of 1 gram per mole hydrogen. So that in turn gives us 9.7 moles of hydrogen. Finally, would anyone like to cap off this section of our discussion by sharing their calculated moles of oxygen? How many moles of oxygen do we have in our sample? 3.225, exactly right. We take our moles of oxygen, which is 51.6 grams. We divide by our molar mass, which is 16 gram per mole oxygen. 51.6 over 16, and that gives us 3.225 moles of oxygen. Perfect. Okay, now all we have to do is put this together, and I'd like us to share our mole to mole ratios, remembering that we prefer to divide by the smallest moles. And we want to take our mole to mole ratio dividing by the smallest number of moles. So in this case, I'd like us to indicate which element has the smallest number of moles. Which element has the smallest number of moles? What are we going to divide our moles by when we take our mole to mole ratio? Carbon, hydrogen, or oxygen? We can pick carbon or oxygen. So let's arbitrarily pick carbon. So then let's calculate our mole to mole ratio. So what is the mole to mole ratio of hydrogen to carbon? Let's calculate that now. What is
3.
the 3 to 1? Yep, exactly right. We have 9.7 moles of hydrogen. We have 3.225 moles of carbon. Not quite 3 in this case. It's 2.79 moles of hydrogen per 1 mole of carbon. Okay. Let's look at the ratio for the moles of oxygen per mole of carbon. In this case, what's our ratio of oxygen to carbon?
1 to 1.
1 to 1. So we have 1 mole of oxygen for every 1 mole of carbon. Okay, let's take a look now. So our molar mass is 62.07. I'm just going to put that as a note. Okay. So now looking at our moles. Oh, the ratio of hydrogen to carbon is 3.00. Okay. So we can write out an empirical formula of C1 because we have 1 mole of carbon, H3 because we have 3 moles of hydrogen, O1 because we have 1 mole of oxygen. So CH3O would be our empirical formula. Now that we have the molar mass and we know that our molar mass is 62.07 gram per mole, we have enough information to calculate our molecular formula. So what is the mass of this empirical formula unit? What is the mass of CH3O? Would anyone be able to share that in the chat?
31.
31. We have 12 grams from carbon, 1 gram times 3 from hydrogen, and 16 grams from oxygen. So we have 12 plus 3 plus 16. That gives us 31 gram per mole. From here, we can calculate N. So what would N be in this case?
2.
2, exactly right. We have 62.07 gram per mole, which is our molecular mass, divided by the mass of our empirical formula unit. And that in turn gives us an N value of 2. Thus, our empirical formula would be C2H6O2 because we've taken each of our subscripts and we've multiplied them by 2. Does that make sense to everyone? Any questions? Okay, so let's keep going now and let's do another example. This time, now that we've had some practice calculating the empirical and molecular formula, we're ready to work on an example with a little bit more independence. So let's give everyone about 5 to 6 minutes and let's work through the following example. We're given the amount of nitrogen, hydrogen, and oxygen in this sample. And we're asked to determine the empirical and molecular formula of this compound. So when we work through this example, I'd like students to share their proposed responses in the chat verbally or annotated on the class whiteboard. And if there are any questions as we work through this example, don't hesitate to ask. I'd like to see students sharing any step of their calculations or their final empirical and molecular formulas that they've calculated. So let's work through this example. And of course, if there are any questions, don't hesitate to ask. So as we work through this example, does anyone have some initial thoughts or ideas that they'd like to share? So would anyone like to share their initial thoughts in terms of the mass of each element or the moles of each element? I mainly just want to get a sense of how students are progressing through this problem, or if anyone would like to share their work as an annotation on the class whiteboard, that would be invaluable for advancing our discussion. So as we work through this example, would anyone like to share some of their calculated mass or mole values? Or as we work through this example, are there any questions I can address or parts that I can clarify? We're starting to try to develop a little bit of independence when solving these empirical formula problems. But of course, if there are any questions or parts I can provide clarification on as we work through this example, don't hesitate to ask. So to provide a little bit of guidance here, I'm going to ask the class to begin to share some responses. So we have one student sharing that they calculated 35 grams for nitrogen. We have a percentage of mass percentage of nitrogen is 35%. We also know nitrogen has a molar mass of 14 gram per mole. For hydrogen, we have a mass percentage of 5.04% with a mass of 1 gram per mole. Oxygen, we have a percentage of 59.96% with a mass of 16 gram per mole. From here now, students have calculated the mass of nitrogen, hydrogen, and oxygen. The mass of nitrogen was obtained by taking the mass percent times the total mass, where we're assuming 100 grams as our total mass. Okay, that in turn gives us 35 grams of nitrogen. We also have students sharing their mass of hydrogen as 5.04 grams. To show how the students obtained that value, they took the mass percentage over 100% times the total mass, which is 100 grams. That gives us a mass of hydrogen of 5.04 grams. Finally, they calculated the mass of oxygen as 59.96 grams. So we have our mass percentage of 59.96% over 100% times 100 grams. And that in turn gives us a mass of oxygen of 59.96 grams. Okay, so we're making progress. My next question for everyone is, what are the moles of each element? How many moles of nitrogen, hydrogen, and oxygen do we have? If anyone would like to share their final calculated values or their final empirical formulas, I already saw that first shared empirical formula in the chat. Let's try to get a few more empirical formulas shared, and then we'll discuss this example. In the meantime, to help provide a little bit of scaffolding, let's work through each of the steps for this process. And I'd like students to help contribute their calculations and responses as we work through this empirical formula problem. So, given that we have the mass of nitrogen, hydrogen, and oxygen, would anyone like to share their calculated mole values? Would anyone like to share their calculated mole values as we work through this example? So we have a calculated mole value of 2.5 moles of nitrogen. This was obtained by taking the mass of nitrogen, which is 35 grams of nitrogen, over the molar mass, which is 14 gram per mole. That in turn gives us 2.5 moles of nitrogen. Okay, what about hydrogen and oxygen? Would anyone like to share their calculated values for hydrogen and oxygen? We have a calculated moles of hydrogen of 5.04 moles of hydrogen. That's obtained by taking the mass of hydrogen, which is 5.04 grams, over the molar mass, which is 1 gram per mole. That gives us 5.04 moles of hydrogen. For oxygen, we have a student sharing that they calculated that we have 3.7475 moles of oxygen. That was obtained by taking the mass of oxygen over the molar mass of oxygen, which is 16 gram per mole. So we have 59.96 over 16, and that gives us 3.7475 moles of oxygen. Okay, so then now I'd like students to share their mole to mole ratios, keeping in mind that it's often best to divide each of your moles by the smallest number of moles. So would anyone like to share a few of the mole to mole ratios that they've calculated? Would anyone like to share their initial mole to mole ratios? You don't have to convert them to whole numbers just yet, just the raw calculated values. So we know the moles of nitrogen are the smallest number of moles. So if we look at the ratio of the moles of hydrogen per mole of nitrogen, for example, what is our mole to mole ratio of hydrogen to nitrogen? About 2.01, right? So we take our moles of hydrogen and we divide it by the moles of nitrogen. We have 5.04 over 2.5, and that in turn gives us a ratio of 2.016 moles of hydrogen per 1 mole of nitrogen. Okay, what about the mole to mole ratio involving oxygen? How many moles of oxygen do we have per mole of nitrogen? What's our mole to mole ratio? About 1.5, right? We take our moles of oxygen, which is 3.7475 moles of oxygen, over our 2.5 moles of nitrogen. That in turn gives us 1.499 moles of oxygen per 1 mole of nitrogen. Okay, so now that we have each of our mole values, so we have 1 mole of nitrogen, we have 1.5 moles of oxygen, and we have 2 moles of hydrogen. So what whole number do we need to multiply each of our moles by in order to get a whole number empirical formula? So we have 1.5, 0.5. What do we need to multiply our moles by to get a whole number? We'd multiply by 2. So that in turn gives us an empirical formula of N2H4O3. Okay. We know our molecular weight in this case is 80.06 gram per mole. And let's look at the empirical formula. The mass would be 12 times 14 for nitrogen, 4 times 1 for hydrogen, and 3 times 16 for oxygen, which gives us an empirical mass of 80 gram per mole. Thus, in this example, the empirical and molecular formulas are identical. Does this example make sense to everyone? Is everyone feeling a little more comfortable calculating empirical and molecular formulas?
Yes.
Perfect. Okay, so let's do one more example. This time we have a compound that contains phosphorus and oxygen. We're given the mass percentages as well as the molar mass, and we're asked to determine the empirical and molecular formula and then name the compound. So let's try to use this example almost as our capstone, and let's apply what we've learned to the following problem. So as we work through this example, I like everyone to share their empirical and molecular formulas, and I'd like students to share their work as they work through this example. So we'll spend about 6 to 7 minutes on this example. And again, I'd like, if possible, for students to share their work in the stepwise method, so that way we can help advance our class discussion. So we have one student sharing their calculated mass of phosphorus. So we know the percentage of phosphorus is 56.4%. We know phosphorus has a mass of 31. Let me double check really quickly. And let's try not to round too heavily. Looking at the periodic table, phosphorus has a mass of 30.9 gram per mole. Okay, this is for phosphorus. For oxygen, our mass percentage is 46.3%, and oxygen has a mass of 16 gram per mole. In terms of calculating the mass of phosphorus and oxygen, assuming 100 grams total, we see that the mass of phosphorus is 56.4% over 100% times 100 grams. That gives us a mass of phosphorus of 56.4 grams. For our mass of oxygen, we have 46.3% over 100% times 100 grams. That gives us a mass of oxygen of 43.6 grams. Okay. Would anyone like to share their next steps in this calculation? How many moles of each element do we have? And what are the mole to mole ratios. Or if there's a question I can address to advance this discussion, also don't hesitate to ask. Would anyone like to share their calculated mole values or mole to mole ratios? So we know the mass of phosphorus and oxygen, and we know the molar mass. Would anyone like to share their calculated mole values or their calculated empirical formulas? So for the moles of phosphorus, we have one student sharing their response. So let me translate that onto the class whiteboard. For the moles of phosphorus, we calculate the moles of phosphorus by taking the mass of phosphorus over the molar mass. That in turn gives us a moles of phosphorus of 1.825 moles of phosphorus. Okay. What about the moles of oxygen? What about the moles of oxygen? How many moles of oxygen do we have in this sample? About 2.725. This is obtained by taking the mass of oxygen, which is 43.6 grams, over the molar mass of oxygen, which is 16 gram per mole. That in turn gives us a moles of oxygen of 2.725 moles of oxygen. As we only have two elements, we're going to take the mole to mole ratio. So we're going to look at the moles of oxygen per mole of phosphorus. That in turn gives us 2.725 moles of oxygen over 1.825 moles of phosphorus. And that in turn gives us a ratio of 1.5 moles of oxygen per 1 mole of phosphorus. One thing I'd like to point out, you can also use the formula method. And using the formula method for the moles of oxygen or moles of phosphorus, we take the percentage of oxygen, which would be 43.6, over the molar mass, which is 16 gram per mole, times the molar mass of phosphorus over the mass of percentage of phosphorus. And that gives us the same answer. So if you're comfortable with the formula method that I presented earlier, it can get you to the mole to mole ratio a little bit more efficiently. So now that we have our mole to mole ratio, we need an empirical formula. So we know we have 1.5 moles of oxygen, and we know we have 1 mole of phosphorus. So what whole number do we need to multiply our moles by to get a valid empirical formula? Two, exactly right. So that in turn gives us an empirical formula of P2O3. So we know that the molar mass and our molecular weight we know that our molecular weight was 220 gram per mole. Okay, so what is the molar mass of this empirical subunit? What is the molar mass of P2O3? Let's tie everything together and let's complete this problem. What is the empirical mass of P2O3?
Oh, 109,494.
Okay, exactly right. So we have 30.9 gram per mole for phosphorus times 2 plus 16 gram per mole for oxygen times 3. So we have 30.9 times 2 plus 16 times 3. That gives us 110 gram per mole. So with this information in mind, what would N be?
2.
2, exactly right. So we take 220 gram per mole divided by 110 gram per mole. That gives us an N value of 2, which would give us a formula of P4O6. Does that make sense?
Yes.
Perfect. So the remaining parts of this chapter are just some additional examples that I've provided and worked out in a video. They cover examples of empirical formula calculations and some basic combustion analysis problems. So what we'll do during the remaining part of this class session is we'll work on some of these more complex examples, and we're going to skip the polymer example because it's a repetition. I do want to talk a little bit about one application of empirical formula calculations, which is this idea of metal combustion. So in metal combustion reactions, we take a sample of metal and we react it with oxygen to generate an oxide. This oxide can be thought of as having a formula of MXOY. So it has a certain number of metal atoms and a certain number of oxygen atoms as part of the formula. Now, if you know the mass of metal and the mass of oxide, we actually have enough information to calculate the empirical formula. So the first step in this is to think about what's actually happening in this reaction. Suppose we have the mass of metal. So this is our initial mass of metal. If we allow our metal to react with oxygen and we get our metal oxide out, by conservation of mass, any mass that ends up in our metal oxide must come from the metal or oxygen. So our metal oxide consists of some mass of oxygen and some mass of our metal. So then, from this picture, we can see we can solve for the mass of oxygen by taking the mass of our metal oxide minus the mass of metal. Okay, so now we have the mass of metal and we have the mass of oxygen. Okay, so with both of our masses obtained, if we have both of our masses on hand, we can calculate the moles of each element and in turn calculate the empirical formula. So in this case, reading through this problem, the mass of our metal was 2.0 grams. The mass of our oxide was 4.31 grams. Thus, if we're solving for the mass of oxygen, we take the mass of oxide minus the mass of metal. That gives us a mass of oxygen of 2.31 grams. Okay, so the mass of oxygen is 2.31 grams. And the mass of metal was found to be 2.00 grams. Okay, now if we want to calculate the empirical formula, we need the mole. And we can calculate the moles of each element given the mass and the molar mass. We know the molar mass of lithium is 6.99 gram per mole, and we know the molar mass of oxygen is 16 gram per mole. So then we can calculate the moles of each of our elements. In this case, our metal was stated in the problem to be lithium. So we can calculate the moles of lithium by taking the mass over the molar mass. So 2/7, we have 0.2857 moles of lithium. We can also calculate the moles of oxygen by taking the mass of oxygen over the molar mass. So we have 2.31 over 16. That gives us 0.144 moles of oxygen. Now that we have the moles of each element, we can calculate our mole to mole ratio. So taking the moles of lithium over the moles of oxygen, we have 0.2857 moles of lithium over 0.144 moles of oxygen. That in turn gives us 2 moles of lithium per every 1 mole of oxygen, which gives us an empirical formula of Li2O, which we could have predicted already just using our charge rules. Does this example of calculating the empirical formula via metal combustion make sense to everyone?
Yes.
Perfect. So let's try to apply what we've learned and let's try to work on the following metal combustion example. And this will be our last example for today. So we have a 3.94 gram sample of cobalt metal that was burned in the presence of oxygen to produce 5 grams of a cobalt oxide compound. Given this information, I'd like us to calculate the compound's empirical formula. So as we work through this example, I'd like us to share our responses in the chat, verbally, or annotate it on the class whiteboard. And I really find breaking things into steps can help make things easier. So we have the mass of metal, we have the mass of metal oxide, and we can calculate the mass of oxygen. So let's share our initial thoughts here. What is the mass of metal? Let's just highlight the attainable pieces of information. What is our mass of metal, which in this case is cobalt? What mass of metal do we have? Yep, 3.94 grams. Okay, and what is the molar mass of cobalt? So if we look in the periodic table and we find cobalt, what is the molar mass of cobalt?
$58.9.
Okay. Okay. Let's also consider what is the mass of our metal oxide. And because it's a transition metal, we don't know the formula of our metal oxide just yet. But what is the mass of metal oxide? Just reading through this problem.
5.0.
Okay. Now, from this information, what is the mass of oxygen in our sample?
1.06.
Exactly right. We take the mass of metal oxide minus the mass of metal, and that gives us the mass of oxygen, which is 1.06 grams. And we know the molar mass of oxygen is 16 gram per mole. So with this information in mind, let's try to calculate the moles of cobalt and the moles of oxygen. So how many moles of cobalt do we have in our sample, and how many moles of oxygen do we have in our sample? So we know the mass of cobalt and we know the molar mass. So how many moles of cobalt do we have? So we know the mass of cobalt. We know we have 3.94 grams.
Over the molar mass. Okay.
Molar mass is 58.9 gram per mole. So how many moles of cobalt do we have? 3.94 over 58.9. And that gives us what?
Okay. 0.06689.
Exactly right. Okay, so we have our moles of cobalt. What about our moles of oxygen? How many moles of oxygen do we have?
.06625.
Exactly right. We take the mass of oxygen, which is 1.06 grams, over the molar mass, which is 16 gram per mole. We have 1.06 over 16. That gives us 0.06625 moles of oxygen. taking our mole to mole ratio, so our moles of cobalt per mole of oxygen, we have 0.0689 moles of cobalt over 0.06625 moles of oxygen. And that gives us a 1-to-1 ratio where we have 1 mole of cobalt for every 1 mole of oxygen. So our ending formula would be cobalt oxide. Does this make sense to everyone?
Yes.
Perfect. So, any questions on empirical formula calculations and molecular calculations, as well as metal combustion analysis? Is this process making a little bit more sense now that we've done a fair number of examples? Is everyone feeling confident that they can calculate the empirical and molecular formula? So if we don't have any other questions, what we'll do is we'll archive